So thank you for the organizer to be here in this session. It was originally, my paper was in fact in another session, but we have no place, but we are really pleased to speak after Gary. So I will now speak more on the numerical things that we have to do to compute things in mechanics, and I will give mostly three techniques that we can use to obtain some numerical integrators that take care of geometrical properties. The first one will be to make a sort of preservation of the configuration space. Then we will move to the variational integrator, and I will end my presentation with the method based on generating functions, Jacobi series. Okay, so the main problems if we deal with manifolds is to stay in the manifolds, and when you have some curved manifolds, then you have to define a specific way of derivatives that depends on the tangent plane. So you have to take care of things when the manifold is not flat anymore. So let's see how we can treat mechanical systems governed by differential first equation, the differential equations. And so the idea is to fix the idea, we will just consider homogeneous group where you are able to move from any point to another one with a certain element in a group. Imagine a rotation, you can move from a point in R3 to another one through a certain rotation, for example. So the problem is now this homogeneous space is not flat, so you have to take care of the derivative of the systems. So the idea is to use the exponential map to give a certain extension, a certain representation of the element of the groups. So if you know certain vectors in the tangent place at the end in the identity, then you are able to compute a certain point in the group through these vectors. Okay. So the idea is to translate the differential equation ODU through something that is flat. So to do that, we use the exponential map, and also its derivatives. So we need the tangential maps of this. So if now we compute where is the spot? Right here. We compute the time derivative. We see that we have to compute the time derivative of certain element in the group. If we multiply by the identity here, then we can recognize here y. Then you can also see that it's a right multiplication by j minus 1. So it's a sort of translation by j minus 1 of the velocities. So you can inject here the derivative of the tangential map. So if you define the derivative like translations in addition to the tangential map in this, then you are able to rewrite the original equations in this way. And if you know this operator, then you are able to obtain by inversions certain equations that now live in the Lie algebra, not the dual Lie algebra, in the Lie algebra, excuse me. So now you can use classical numerical methods. For example, yes. Yes, so you have to inverse this operator. So it's well known that we are able to develop this operator in a certain time of the adjoint operator with with Bernoulli numbers. Then you can use some Runge-Kutta methods to find the solution xi. Non, c'est pas dans ce sens-là, c'est dans ce sens-là. So I want to be quick, and at the end you will obtain xi. With xi you can obtain the element of the group at each time, and then you are able to reconstruct the solution y. As an example, the Fourier body is used, and we used it because we have analytical solutions. So the Lie group is the group of rotations. Sometimes it doesn't work. And so we can. So it is classical to the analytic solutions are in with this line. This is the RMK method for Runge-Kutta methods of the three orders compared to another variational methods. So as you can see, you stay in a manifold, which is represented by the sphere, but you make some error, and mostly in the energy. The energy is not conserved with the RK-MK for methods. So we have now preserved the configuration space, but some things are missing. So the other idea is to use variational integrator. And the main idea is to, when you are in the continuous parts, you are dealing with a Lagrangian, then you will obtain the Euler equations, like we see in the preceding presentations. And then you can do exactly the same thing in the discrete parts. But usually, the classical methods do it like this. You obtain continuous Euler-Lagrange equation of motion, then you discretize them to obtain a sort of discretized Euler equations, a sort of numerical algorithm. So the idea is to first discretize the Lagrangian, then to obtain a discrete Euler-Lagrange equations. And this time, if you have symmetries and Noethel theorems, can still be obtained in this way, but not obligatory in the other way. So, so the idea is to start from a Lagrangian, which is a sum of discrete Lagrangians, which depend on the velocity vectors belonging in the Lie algebra. I will go really quick. And the idea is to move from a point to another through a certain variable psi, which is belongs to the Lie algebra. So if you to go to another to one point to another one, you will use a certain function tau that depends on psi. And as you see, if you are computing the variation, some calculus, the variational calculus, you have to compute the variations of the Lagrangians and something on the on these variables. So if you make calculations, and you will do it, we'll go quickly on this, but everything is on the paper. So, and it's really classical. Then you will obtain a relationship between a certain variation of that intervene in the Lagrangian, the variation of the Lagrangians, and it could be related to the adjoint operator. Okay. So at the end, if you introduce a sort of momentum here by this operator, then you are able to write a discrete Euler-Poincare equations. And the thing's importance is now, if there is some symmetry, and if there is some things that are supposed to be preserved by the continuous systems, then the numerical systems with this algorithm will confirm and guarantee the invariances. So this is the numerical algorithm. We start from certain points in a certain directions. And then we have to compute at each time these things and to solve a nonlinear equation. And then we have to update the position. Okay. The things really important is that we can also adapt those techniques, but it will have to be, it is a big job to do, big work to do it, to extend it to in a multi-symplectic context. Since we start from a variational calculus, and so we are doing to do this job with my PhD student, Pierre Carré. Okay, so let's move to method based on generating functions. So the main idea is to, I don't know how many times I have, Jerry? 7 minutes. Okay. So the main idea is to say that a canonical transformation can be viewed as a numerical method, since you can pass from a point to how do you say it in English? Well, to a point to another one. Since the canonical transformations preserve the pre or simplistic two forms, that the main property, geometric property, will be guaranteed. Okay, and you can also generate lots of numerical methods, since to each generating function you can construct a canonical transformation. So the main idea is to make a sort of change of coordinates. Let's imagine that you have the space phase with two coordinates and the time, q and the positions and the moment and the momenta. And we want to move it to a certain other coordinates, capital Q and capital P. And it's well known that when you are constructing canonical transformation, you can make a sort of intermediary transformation with mixed variables. And so you have the new variables in here and the old for the position. And the main idea, it should be little omega, is to guarantee that when you push forward the symplectic form from here to here in those transformations, then the two you will have an invariances. So this is sort of transformations of giving capital P by these two, and F is also a transformation which gives little q by these things. So if you compute this, and you want to, you have two Poincaré Cartan forms, the one with the little variables and the one with the big variables, and two Hamiltonians, h and k. If you make the differentiations of the Poincaré Cartan form, you will obtain the symplectic forms. So you have to push forward, no, pull back the two forms by those two transformations f and h and f. So if you do that, you can also, and since the operator d and the push forward commute, then you will have this, for the invariance of the two symplectic forms, you will have these relationships. So the difference of these two should differ by a certain closed form. Let's say that ds is this closed forms. Then we can write it in this special case to compute the second kind of generating functions. And if you make these computations and you put all the main different forms in factors, then you will obtain three conditions, one on the concerning the time, one concerning the momentum, and one concerning the positions. And it happens that whatever you can choose any function g, and you will obtain by its partial derivative a new Hamiltonian and a new function and a sort of implicit way to compute the new momenta. 2 minutes. So now the main things to do is to suppose that we want to have a new Hamiltonian that is really that vanish. If we do so, then we will obtain an easy system to integrate. So at the end, we will have to fit this equation, and then the future numerical algorithm will be given by this the derivatives of the generating functions. So with 2 minutes, the important thing is now that if k is 0, then the system is really easy to integrate. We have a straight line, the momentum are constant, and the position will be also constant. Okay. So the main idea is to start from generating functions that we can write like this. And this is when you use this generating function, you do nothing. H is 0, and the change of variable is simply the identity. So if you perturbate this generating function by a sort of on-off and that, then you can find, depending on the number of here m that you stop this sum, you can obtain many numerical algorithms. And the first one is the well-known Euler symplectic numerical methods. The thing that is really important, this is really, is that if we start from an initial Hamiltonian system, then we can obtain an exact solution. But with the numerical solution, with the numerical method, we will obtain a numerical solutions. And the question could be, from which Hamiltonian, numeric approximately Hamiltonian, this is an exact solution. So this is the backward analysis questions. we can do exactly the same thing using Poincaré quartant equations. And now we have to make some more works using the Poincaré quartant in the Lie groups context. That means that we have to do exactly the same thing and to compute the invariance between a change of coordinates to compute a canonical transformation. It was done by Marsden, and we also have, well, some calculations are a little bit more not so straightforward. But at the end, we will obtain a numerical methods that are guarantees in the discrete configurations that the main property of the system, the physical system, will be guaranteed. Thank you very much.
Discussion is open. When you want to integrate numerically the Hamilton-Jacobi equation, it is a partial differential equation. You need some boundary conditions. Which boundary condition do you use?
You mean in time? Yeah.
I don't know. Hyperbolic?
In fact, it's integrated analytically, like this. We suppose that the generic function is written like this. Yes. Then we put these solutions into the Hamilton equation Jacobi's, and we obtain some coefficients. Maybe we can check the initial condition are important, I think. Yeah, you're right.
Another question? So, thank you very much.
Merci.